Hey there, science fans! Have you ever wondered what holds everything together? I'm not talking about gravity, but something much smaller, something happening at the level of atoms and molecules. The answer lies in molecular bonds. Molecular bonds are like tiny forces of attraction that hold atoms together to form molecules. These bonds are essential because they determine the properties of substances and how they behave. Everything from the water we drink to the air we breathe, even the DNA that makes us who we are, is shaped by the power of molecular bonds. Without molecular bonds, our universe would be a very different place, a chaotic soup of individual atoms. Instead, these bonds create the molecules that make up everything around us, giving structure and stability to the world as we know it. So buckle up as we dive into the fascinating world of molecular bonds and explore the different types that govern the interactions between atoms. Let's start our journey with a type of bond based on a classic principle: opposites attract. This is the driving force behind ionic bonds. In an ionic bond, one atom, eager to achieve a stable electron configuration, donates an electron to another atom that's equally happy to accept it. This exchange creates two ions, a positively charged cation, the donor, and a negatively charged anion, the acceptor. These opposite charges are irresistibly drawn to each other, forming a strong electrostatic attraction, the ionic bond. A classic example of an ionic bond is found in table salt sodium chloride. Sodium readily donates an electron to chlorine, forming Na+ and Cl ions that stick together like magnets. This simple process of electron transfer and electrostatic attraction is the basis for the formation of many salts and minerals, showcasing the power of opposites attracting in the world of chemistry. Now let's talk about a different kind of bond, one built on sharing rather than transferring electrons. This is the covalent bond, a type of chemical connection where atoms share electrons to achieve a stable electron configuration. Think of it like two friends sharing a toy to complete their collection. In a covalent bond, the shared electrons spend time orbiting both atoms involved, creating a strong bond. But covalent bonds come in different flavors. Sometimes the sharing is equal, with electrons spending an equal amount of time around each atom. We call this a nonpolar covalent bond, and it occurs when the atoms involved have similar electronegativity, their tendency to attract electrons. However, if one atom is a bit greedier for electrons, it pulls the shared electrons closer, creating a polar covalent bond. This results in a slight separation of charge, with one end of the bond being slightly negative and the other slightly positive. Water is a prime example of a polar covalent bond. The oxygen atom, being more electronegative, hogs the electrons, giving it a partial negative charge, while the hydrogen atoms become slightly positive. Understanding the difference between polar and nonpolar covalent bonds is key to comprehending many chemical reactions and biological processes. Now let's move on to some weaker players in the world of molecular interactions. Metallic bonds, as the name suggests, are responsible for holding metal atoms together. In metals, the outermost electrons are loosely bound and free to roam around, creating a sea of electrons that flow freely throughout the material. This unique arrangement gives metals their characteristic properties, such as high electrical conductivity, malleability, and ductility. Then we have hydrogen bonds, a special type of dipole-dipole attraction that occurs when a hydrogen atom is bonded to a highly electronegative atom, like oxygen or nitrogen. These bonds are weaker than ionic or covalent bonds, but they play a crucial role in many biological systems, including holding DNA strands together and determining the properties of water. Finally, we have the very weak van der Waals forces, which arise from temporary fluctuations in electron distribution within molecules. These forces are responsible for the attraction between nonpolar molecules and play a role in phenomena like gecko feet sticking to surfaces. While individually weak, these forces, when combined, can significantly influence the properties of materials and the behavior of biological systems.